Hi, this is Babak. In this video I'm going to continue my discussion on mathematical induction from a theory point of view. This is the third lecture in this series of lectures. First, let me have a quick review of what I'm going to cover in this video. First, I introduce you another variant of mathematical induction known as the general principle of mathematical induction, or GPMI for short. Then, I will use the well-ordering principle WOP to present a proof for the validity of this GPMI. After that, I present a simple example to show how GPMI can be employed in practice to prove statements involving natural numbers. Then, I introduce you another variant of mathematical induction known as the strong principle of mathematical induction, or SPMI for short. For this principle, I present two different proofs. One proof, I will only use the well-ordering principle to show the validity of SPMI. In the second proof, I use only the principle of mathematical induction that we covered in the first video to present a proof for the validity of SPMI. And finally, I will present a simple classic example to show how SPMI is employed in practice to prove statements involving natural numbers. Okay, now let me introduce you this variant of mathematical induction, the general principle of mathematical induction, GPMI. But before reading the statement and presenting the proof for that, let me motivate you why one might need the general principle of mathematical induction in the first place. As I will show you in the next coming example, there are cases that a predicate P of n involving natural number n is not true for, say, n equal to 1 and n equal to 2. For example, you have a statement, you have a predicate. When you check the validity of this predicate for n equal to 1, you see that this is a false statement. When you check it for n equal to 2, you get a false statement. But suddenly when you check it for 3, for 4, and etc., it seems to be a true statement, okay? So you have this motivation that might be this predicate, even though not true for n equal to 1 and n equal to 2, but it seems to be valid for all the rest of the natural numbers, yes? And hopefully you have been convinced so far by now that this mathematical induction is a very powerful tool in the hand of a mathematician to prove statements involving natural numbers. So, the first thing that comes to mind, we don't want to ignore such a powerful tool because of this very minor problem. And then the general principle of mathematical induction actually amend this problem and try to use this powerful tool for this case as well. So that's the motivation behind the general principle of mathematical induction. Now let me read the precise statement and present the proof for that. General principle of mathematical induction. Let P of n be a predicate involving the integer n with the following properties. Number 1, P of n node for some integer n node is true. For every integer k greater than or equal to a node, if P of k is true, then P of k plus 1 is true. Then P of n is true for all integers n greater than or equal to a node. So you see the difference in the base of induction here. In the normal PMI, principle of mathematical induction, the base is to show P of 1 is true. But here we are concentrating on a different number, and I am also assuming that this number is an integer because I want to consider the most general case. So even this n node can be a negative integer, it doesn't matter, as you see in the proof. Okay, the second one is somehow similar to the previous one, but it is also different a little bit, so you need to know that. In the normal mathematical induction, we need to consider that this P, we need to assume that P of k is true, and then we need to show that this implies the next one, p of k plus 1, is true, and we have to do this for all integers, sorry, for all natural numbers k. But here we want to do the same thing. We want to show that the truth of p of k implies the truth of p of k plus 1, but not for all natural numbers k, for all integers such that that integer is greater than or equal to n node. And then if we succeed to show the validity of 1 and 2, the first item and the second item, then what I can conclude in the best scenario is that p of n is true for all integers, not for all integers, sorry, for all integers n greater than or equal to n node. Okay, so we cannot evaluate the truth of p of n for n less than n node. So if I can do this, if I can do that, the only thing that I can infer from these two items is that the p of n is true for all integers greater than or equal to this n node, the starting point. Okay, now let me present the proof of this, and then I will present a simple example to show how this will work in practice. So as I mentioned in the overview, I want to use the WOP, the principle of well-ordering principle of natural numbers, to present a proof here. And the proof is very similar to the proof of the PMI, so I need to just adjust it a little bit so that it can be fit into this new problem. Okay, so proof is, I would say, let. So if you remember, in the proof of PMI, I introduced you a set consisting of all natural numbers such that p of n is false. And then we showed that A is empty by using proof by contradiction. Now I want to adjust this set in this problem a little bit by doing a shift in what I am writing here. Okay, so let A be the set of all natural numbers such that p of n plus that n node minus 1 is false. Okay? So I have done this shift of n node minus 1. So we show that A is empty. If not, and if A is not empty, then what we have? You are saying that A is not empty, and the way that I constructed A, I see that A is a subset of the natural numbers, because I am saying that A is the set of natural numbers satisfying an extra condition. So A is definitely a subset of n. So if you now remember the well-ordering principle here can be used to conclude that the set A has a minimum. So I would say let A, little a, be the minimum of this set. Okay, then, so what is the meaning? When you say that A is the minimum of this set, first of all, it means that this element, this A, belongs to my set. And when A belongs to my set, it means that this satisfies these two criteria. Okay? These two conditions. So it means that I can conclude that A is a natural number in the first place, and I can conclude that when I replace this n with this A, what I get is a false statement. So it means that P of A plus n node minus 1 is false. So let me put this in a box. I want to refer to it later. Okay. Now, what I want to first tell that is this little a is not equal to 1. Yes? Why is that the case? A is not equal to 1 since otherwise we have, so if a is equal to 1, then this statement with p of 1 plus n node minus 1 is false. So this means that so here minus 1 and 1 are cancelled, so this means that p of n node is false. But this is not true, yes? Because we learned that p of n0 is true. So this cannot happen. Okay, so this is the reason that a is not equal to 1. A is not equal to 1, and now you are telling me that a is a natural number. So I immediately conclude that a is greater than 1, and so this means that a, so let me write it in this way, a minus 1 is a natural number. Okay. On the other hand, you know that a minus 1 is smaller than a, strictly smaller than a, and you know that this little a is the minimum of my set. So this implies that a minus 1 is not in my set. Yes? Because a is the minimum of my set, and a minus 1 is strictly smaller than this one. So a minus 1 is not in the set. The reason for that might be two cases, yes? Either a minus 1 might violate the first condition, or it might violate the second condition, or of course both, yes? But a minus 1, already we saw that it is in the set of natural numbers, so a minus 1 cannot violate this part. So a minus 1 has to violate this part, otherwise a minus 1 will be a member of my set. So this means that if I replace this n with a minus 1, this will be violated. But violating this is false, this means that this will be true. So this means that p of a minus 1 plus n node minus 1 is true. Yes? So I realize that a minus 1 should violate this. It means that if I replace n with a minus 1, this statement should be violated. So it means that this statement should be a true statement. Violating a false statement here, I mean to be true, yes? And then let me simplify this a little bit. So this means that p of a plus n node minus 1 is 2 is false. Oh, sorry, is true. Okay? But let me see what is this number here. So I know that a is a natural number greater than 1. Yes, so we learned that a minus 1 is a natural number, so a is greater than 1. Okay, so I want to show that this is an integer. This is an integer greater than or equal to n node. Yes, is that true or not? So what I need to show is to show that a is greater than or equal to 2. Yes, when you say that a is a natural number and you say that a is not 1, so this means that a is greater than 1, so this means that a is greater than or equal to 2, so this means that a minus 2 is greater than or equal to 0, so this means that if I add n node to it, it becomes a plus n node minus 2 is greater than or equal to n node. Yes? So this number that you see here is greater than or equal to n node. Yes? On the other hand, this is an integer. Yes? Because a is a natural number, n node is an integer, 2 is also an integer. So this combination is definitely an integer on the one hand. On the other hand, I showed that this is greater than or equal to n node. Yes? So let me write it here. A plus n node minus 2 is an integer greater than or equal to n node. This is the content. So now we can use the second item here. This tells you that if you have an integer, that integer is greater than or equal to n node, and you know that p of that integer k is true, then you can conclude that p of k plus 1 is also true. So here, this is an integer, this is greater than or equal to n node, and we know that this is true. So this implies that, so therefore, p of a plus n node minus 2 plus the next plus 1, which is of course p of a plus n0 minus 1, is true. But this is contradiction. You see, here I found that p of a plus n node minus 1 is false. Here I learned that p of a plus n node minus 1 is true. So this contradicts the statement p of a plus n node minus 1 is false. Okay, so therefore this assumption that a is not the empty set gives rise to a contradiction. So it means that we have to admit that a is equal to the empty set. Okay. Now I want to show that if you choose n to be an integer greater than or equal to n node, then p of n is true. To prove this, I used the proof by contradiction again. Okay, let me write this in detail. We now show that we make it a little bit bigger. We now show that for all integers n greater than or equal to n node, p of n is true. Assume that this is not the case. And there exists an integer greater than or equal to n node such that p of m is false. Okay? Now P of m can be written in this form as well. Instead of m, I write m minus n node plus 1 and then plus n node minus 1. First of all, let us see, do you agree with this one or not? So this plus n node and minus n node are gone. This minus 1 and that 1 are gone. What is left for me is pm. So this, what I have written here, is another name for m. But why this is useful? Now let us concentrate here. This, I will claim this is a natural number, and that's very clear because n node was an integer. M is also an integer, but greater than or equal to n node. So this means that this number is a non-negative integer. But if I add 1 to a non-negative integer, definitely this becomes a natural number. So this belongs to the set of natural numbers. Okay, so let me call it n. Okay, let me give this a name. I will call this one n, and I showed that this n belongs to the set of natural numbers. So this is p of n plus n node minus 1. Okay, so what I learned is that p of m, which is a false statement, this means that this is also a false statement because this is exactly p of m. So I would say that p of n plus n node minus 1 is false. And we know that this n belongs to the set of natural numbers. And now if I ask you to which set does this little n belong to, you will immediately answer the set A that we started with. Why? Because you see n is a natural number, so it satisfies the first condition. And on the other hand, p of n plus n node minus 1 is also false, so it means that it also satisfies the second condition. So this means that immediately I can conclude that this n belongs to A. But again, this is a contradiction because just right now I showed that A has to be empty. And this is in violation with this one, okay? Okay, so this means that A is not empty. And this contradicts A is equal to empty. Therefore, P of n is true for all integers n greater than or equal to n naught. Okay. So let me now go and present an example so that you can use this in practice. Okay, now let us consider an example in which the general principle of mathematical induction is helpful to prove this statement. For every natural number n greater than or equal to 5, prove that 2 to the n is greater than n to the 2. Okay, so I think it is instructive if I set up a table so that we can compare the value on the left hand side with the value to the value of the right hand side. Yes, so let us see how this will go. So let me set up a table here, and then here I write n equals to 1, 2, 3, 4, 5. Now let me continue this for the next number, at least 6. And then I calculate 2 to the n, the left hand side here, and I calculate n to the 2 here. So if I plug n equal to 1, this becomes 2, this becomes 1, which of course is true. You see, this one is greater than that one. But let us see what happens for the next values. When I plug 2, the left hand side becomes 4, the right hand side also becomes 4, and now you see that 4 greater than 4 is a false statement, so it doesn't work. And now I put 3, then the left hand side becomes 8, the right hand side becomes 9. Again, 8 greater than 9 is also false, and if I put 4, this becomes 16, this also becomes 16. Again, as you see, this is false again. But if I plug 5, this becomes 32, the right hand side becomes 25. If I plug 6, it becomes 64, and then it becomes 36. And in these two, you see that this is true statement that the left hand side is greater than the right hand side. So according to this problem is claiming that from number 5 onwards, this will not be violated anymore. Okay, even though you see the first statement for n equal to 1 was correct, but for 2, 3, 4 we have false statements, but then this problem claims that from 5 onwards we will have always the case, this would be always the case that 2 to the n is greater than n to the 2. Okay, now let us use the general principle of mathematical induction to present a proof here. So I would say that this statement Pn, my predicate is 2 to the n is greater than n to the 2. Okay, the first thing that we need to check according to this problem is not P of 1, is P of 5. So the base of induction is checking the validity, the truth of P of 5. So P of 5 reads in this way. I need to replace n with 5. So this becomes 2 to the 5 is greater than 5 to the 2. But this statement is equivalent to this statement. 2 to the 5 is 32, and then 5 to the 2 is 25. 32 greater than 25 is true. So we realize that P of 5 is true. Now we say let k be an integer or a natural number. It doesn't matter in this case because I want to say that's greater than or equal to 5. Let k be an integer greater than, so let me write it in this form. Let k greater than or equal to 5 be an integer such that P of k is true. Namely, let k greater than or equal to 5 be an integer such that 2 to power k is greater than k squared. We show that P of k plus 1, which is 2 to power k plus 1 greater than k plus 1 to the 2, is true. So you see, I'm assuming that P of k is true, but for k greater than or equal to 5, an integer 1. So it means that I am assuming that if k is greater than or equal to 5 and it is an integer, 2 to the power of k is greater than k to the 2. I want to show that P of k plus 1 is also true. What is the meaning of P of k plus 1? It means that wherever you see n in your predicate, you have to replace it with k plus 1. So if I replace these n's with k plus 1, I will have this. So I want to show this is true. Okay, I know that this is true, so I can start with this statement. So 2 to the k is greater than k to the 2. My motivation is somehow to conclude this inequality. So the first thing that comes to mind is to change this so that it becomes 2 to power k plus 1. And that's very easy. I just multiply it by 2. Both sides, yes? But what does this mean? 2 times 2 to power k is just 2 to power k plus 1 is greater than 2 to power k squared. So sorry, 2 times k squared. Okay, now what I can see is that 2 to power k plus 1 is greater than 2 to power k squared. But my goal is to show that this expression is greater than k plus 1 to the 2. So for example, I can write this as k squared plus k squared. And then I can write it as k squared plus 2k plus 1, but plus k squared minus 2k minus 1. Why I did this actually? This one, k plus 1 to the 2, is k squared plus 2k plus 1. I want to have this on the right hand side, so I wrote it. But I have to subtract things that I have added, yes? Because now you see that minus 2k and 2k are gone, minus 1 and 1 are gone, so I am left with k squared plus k squared. That's exactly the same thing. So this equality is indeed valid. But now what I can do, I can collect the first three terms into k plus 1 squared, and between these two I can factor a k out. It becomes k minus 2 and then minus 1. But now see here, we know that k is greater than or equal to 5. So k is greater than or equal to 5. So it means that k minus 2 is greater than or equal to 3. And because these are positive numbers, I can multiply them side by side. It gives me k times k minus 2 is greater than 15. So then this means that k times k minus 1 is greater than or equal to 14. So what you see here is an integer greater than or equal to 14. Yes? So this means that this itself is greater than the first part, k plus 1 to the 2. Yes? This number is greater than or equal to 14. If I add a number greater than or equal to 14 to this one, so definitely the whole expression is greater than this one on its own. Okay? Now look here. This one is greater than this, equality up to here, and then again at the end I have this one greater than this. So this means that this is greater than k plus 1 to the 2. Okay, so actually now, so we were able to show that p of 5 is true. We assumed that k is an integer greater than or equal to 5, and then we showed that the truth of p of k implies the truth of p of k plus 1. So now, therefore, the general principle of mathematical induction implies that p of n is true for all integers n greater than or equal to 5. And that was the goal of this example. But before finishing and going to the next topic, I want to mention some point here. You see, because this problem was in such a way that the first one, n equal to 1. So if I ask you, is p1 true or false? You see that p1 is indeed true. Okay? So assume that you wanted to prove the same statement for not n equal to n greater than or equal to 5, but just n greater than or equal to 1. So what you do, you first check p1, and coincidentally it is true. Then you might think that this is valid for all choices of n, so then you will start the proof. Okay, then you assume that p of k is true, which is exactly this one, and then you try to show that p of k plus 1 is true. So what you have done here is exactly the same until the very last step. You can take all these steps up to here, but you cannot go to this one, because if k is greater than or equal to 1 instead of k being greater than or equal to 5, then k minus 2 is greater than or equal to minus 1, so that becomes a negative number. And then there is no guarantee here that this is a positive number, so it means that you cannot conclude the very last step. And then you realize that something is going wrong, and then you can come back and fix the problem. I just want to mention that this proof is actually sensitive to the starting point as well. That was my goal. Okay? Okay, now I want to introduce you another variant of principle of mathematical induction, namely the strong principle of mathematical induction, or SPMI for short. Before formulating this principle precisely and presenting the proofs that I want to introduce here, let me motivate you why one might need this strong principle of mathematical induction in the first place. Assume that you have a predicate p of n involving the natural number n. An inductive step for the principle of mathematical induction that we learned in the first video, you assume that p of k for some natural number k is true, and prove that p of k plus 1, the next one, is true as well. But sometimes, as I will show you shortly by presenting an example, the nature of the problem at hand is such that concluding the truth of P of k plus 1 based on just the truth of the previous step P of k is not straightforward. But if we know instead the truth of all the statements P of 1, P of 2, up to P of k, then it is fairly straightforward to conclude that the next one, P of k plus 1, is also true. This principle, the strong principle of mathematical induction, is an adaptation of the principle of mathematical induction to include these cases as well. Of course, I will present examples so that you will understand. This will illuminate this point for you. But let me now read the statement and present the proof for this statement. The strong principle of mathematical induction. Let P of n be a predicate involving the natural number n with the following properties. Number 1, P of 1 is true. Number 2, for every natural number k, if P of 1 and P of 2 and up to and P of k are true, then P of k plus 1 is true. Then P of n is true for all natural numbers n. Now I want to prove this statement for you, but I will present two proofs for you. I think it's instructive to be familiar with both variants of the proof. One proof relies on the well-ordering principle, WOP, and the other proof relies on the principle of mathematical induction that we learned before. Okay, now let me first introduce you the proof which is based on WOP. So the proof, so let me write it with a different color, based on WOP, the well-ordering principle. Okay, so I hope that you have enough experience now. Again, I want to introduce you a set, and I want to show that this set is a subset of the natural numbers and is not empty, so the well-ordering principle will guarantee that there is a minimum for this set. Okay? And then when I read the last statement, P of n is true for all natural numbers, then immediately becomes clear how to define my set. So I would say let A be the set of all natural numbers such that P of n is false. Okay? As before, we show that A is empty. In other words, you cannot find such a number that turns P of n to be a false statement. And then we are done, of course. If not, and if A is not empty, then on the one hand A is not empty, on the other hand A is a subset of n, then the well-ordering principle will guarantee that A has a minimum element, has a minimum. Okay? Now, let little a denotes this minimum. So let A be the minimum of my set. When you say that A is the minimum of my set, it means that this is indeed an element in the set. And when you see that A is an element of my set, it means that it satisfies these conditions necessary to be an element of the set A. So this means that A is a natural number. Moreover, A should also satisfy this condition. So this means that P of A is false. Okay, so let me put this in a box. I need it later. Okay, now you see here P of 1 is true. So this is clearly not equal to 1, because if A is equal to 1, then this will read P of 1 is false, which is not correct because we know that P of 1 is true. So since P of 1 is true, A is not equal to 1. Now you are saying that A is not equal to 1, and you also know that A is a natural number, so this means that A is greater than 1, so I can write it A is greater than 1, or in other words, so you can say that A minus 1 belongs to the set of natural numbers. Okay, now let M be a natural number. Be a natural number such that a 1 is less than or equal to M is less than or equal to A minus 1. So first of all, this interval of natural numbers is not empty, yes? Because you see that A minus 1 is a natural number, so it means the minimum value that A minus 1 can attain is 1. So even in this case, M between 1 and 1, I have M equal to 1. And if A minus 1 is greater than 1, I will have more options available for M. But what is important, this is crucial to make sure that this interval containing natural numbers is not empty. Okay, now take your minimum value A and subtract it, and subtract M from it, and write A minus M, yes? This is strictly smaller than A, yes, because M is a positive number. And on the other hand, we know that A is the minimum of my set. This little a is the minimum of my set, and A minus M is smaller, strictly less than A, so this implies that A minus M does not belong to my set. But again, there are two possible reasons why A minus M does not belong to the set A. Either it violates the first condition, or it violates the second condition, or both. But A minus M is a natural number. Why? Because I assume that M is a natural number. I assume that M is between 1 and A minus 1. And we know that A itself is a natural number greater than 1. So definitely the difference between these two numbers is a natural number. So this means that the reason that A minus M does not belong to A is not because A minus M violates the first condition. So this means that it has to violate the second condition. So this means that if I replace this N with A minus M, then this should be not true. So it means that P of A minus M is not false. Yes? Why? Because if P of A minus M is false, because A minus M is also a natural number, then A minus M has to be in my set. But now that you are saying that A minus M does not belong to my set, and I know that M minus M is a natural number, there is only one way that A minus M does not end in the set A, and that is P of A minus M is not false. But this sentence means that P of A minus M is true. So let me change my color here. So what we know that if M is an integer, is a natural number, and 1 is less than or equal to M, less than or equal to A minus 1, this implies that P of A minus M is true. This is what we got so far. So let me put this in this. This is not part of the proof, so this is why I changed my color. This is the summary of what we have done so far, to put it in front of our eyes. Okay, now I want to use this over and over again for different values of M that I can choose from this interval. So here, let me choose M equal to 1. Am I allowed to choose M equal to 1? Yes, because it satisfies being natural. It also satisfies this condition. So M equal to 1 is one possible choice for M. And then, regardless of the value of M that I choose from this interval, I realize that P of A minus M is true. So this means that I know that P of A minus 1 is true. Let me choose M equal to 2. This means that P of A minus 2 is true. Okay, and then let me continue, for example, M, let me choose M equals to A minus 2. Then this means that P of A minus 2, which is actually P of 2, is true. Yes? So now you see I have chosen M equal to A minus 2, which is also valid here in this case. And then I would say that, okay, I replace M with A minus 2, and then I simplify that minus A and A are cancelled, minus 2 is 2. And then finally, I will write this for A minus 1 as well. So this becomes P of A minus 1, which in this case is P of 1, is true. So now look what's happening. P of 1, P of 2, up to P of A minus 1 are all true. So you see, I have, so therefore, I have P of 1 is true. So let me write P of 1, P of 2, up to P of A minus 1, and P of A minus, P of A minus, P of A minus 2 and P of A minus 1 are all true. So then I can conclude from here, you see, number 2. If I have a natural number k so that P of 1, P of 2, up to that point P of k are all true, then according to item number 2, I can conclude the next one is also true. Okay, so now you see A minus 1 is a natural number. We have it guaranteed here. And I know that P of 1, P of 2, up to P A minus 1 are all true. So according to the second item, I can conclude that P of the next one is A minus 1 plus 1, which is P of A, is true. Okay? But now this is my contradiction, yes? So why? Because here we learned that P of A is false. Then simultaneously I have to admit that P of A is true as well. So this is a contradiction. This contradicts this statement the statement P of A is false. So this assumption that we made, namely A is not true, is not possible. So it means that A is, if the assumption that we made that A is not the empty set is not possible, so it means that A is the empty set. So therefore, A is equal to the empty set. So it means that if you are looking for a number n for which P of n is false, don't look for it. You will not find it because the set is empty. So it means that for all possible choices of n from the set of natural numbers, P of n is actually a true statement. So this is one proof of this strong principle of mathematical induction based on WOP. And you see that there is just minor changes from the proof that we presented for the principle of mathematical induction itself. Okay? Okay, now I provide an alternative proof for this strong principle of mathematical induction, which relies on the principle of mathematical induction itself. Okay, so let me write it here based on the principle of mathematical induction. The strategy of the proof is in this form. So using this predicate, which is given in this statement of the strong principle of mathematical induction, I construct a new predicate Q of n so that this new predicate satisfies the conditions of the principle of mathematical induction. And then I can use the principle of mathematical induction for that predicate to conclude that for all natural numbers n, Q of n is true. And then when I realize that Q of n is true for all choices of the natural numbers n, I use this fact and show that this is the case for P of n as well. So how should I define my predicate? I would say let Q of n be the predicate defined as follows. Of course, for the natural number n. So I would say that Q of n is defined to be P of 1 conjunction with P of 2 conjunction with up to P of n. Yes? If n is if n is a natural number. Now we show that Q of n satisfies the conditions of the PMI. What do I mean by this? I want to show that Q of 1 is true. This is one of the conditions of the PMI. And then I choose a k in the set of natural numbers and I assume that Q of k is true. Then I showed that this then would imply that Q of k plus 1 is also true. So my strategy is clear. I want to show Q of 1 is true. I assume that Q of k for some k in the set of natural numbers is true, and I want to show that Q of k plus 1 is also true. Yes? Okay. But, so Q1 is actually nothing except of P of 1 based on the definition of Q of n. So when you say Q1, this would be the first term. Q1 is equal to P1, and since P of 1 is true, Q of 1 is true as well. Okay, so this is very simple, just nothing. Q of 1 is the same as P of 1. But now I would say let k be a natural number and let Q of k be true. We show that Q of k plus 1 is also true. Okay, how should I prove this? So you are telling me that Q of k is true. But what is Q of k? Q of k by definition is P of 1 conjunction with P of 2 up to P of k. So you are saying that this is true. So this implies that because Q of K is a conjunction and this conjunction is true, so it means that all these statements involved are all true. Yes? So this means that P of 1 is true, and then you know that P of 2 is true. Okay, I need to write and, of course, and then P of K is true. So and yes. So all of them are true. But now look here. This predicate has this property that if P of 1, P of 2, up to P of K are all true, you can conclude that P of K plus 1 is also true. So therefore, actually this is exactly happening here. Yes, sorry. This is exactly happening here. P of 1, P of 2, up to P of K are all true. So based on the second item, therefore I can conclude that P of K plus 1 is true. Now I knew that P of 1, P of 2 up to P of K were true. Now I realize that the next one, P of K plus 1, is also true. So therefore, hence, the conjunction P of 1 and P of 2 and up to and P of K, and now I can add this one as well, is true. Yes? So I knew that all of them were true. Now I realize that this is also true. So the conjunction of all of them is true. But if I ask you what is this, the answer is QK plus 1. Q of K plus 1. This is the definition of Q of K plus 1. So I realized that the inductive step for Q of N, this new predicate, also works. So I would say thus, based on principle of mathematical induction, Q of N is true for all N in N. But my goal was not to show that Q of N is true for all N. You see, my goal is to show that P of N is true for all natural numbers N. This part of the proof I will do by contradiction, proof by contradiction. Assume that this is not the case. Let me write this in detail. We now show that P of N is also true for all N in N. Assume that this is not the case. And there is a natural number M for which P of that M is false. Then, what is Qm now? Q of M is equal to P of 1 conjunction with P of 2 conjunction with up to P of M. So when you say that P of M is false, so it means that the last statement in the definition of Q of M is false. So regardless of the logical value for the previous statements, the whole conjunction, the whole combination is false. Okay? Then is also false. This is a contradiction, yes? Because we just showed that Qn is true for all N in N. So this contradicts the statement Qn is true for all N in N. Yes? Before finalizing this, let me just mention you. So here, you remember, I proved the Spmi using WOP. So it means that WOP implies Spmi. Yes? Now here I use the principle of mathematical induction and prove the strong principle of mathematical induction. So what does it mean? It means that PMI also implies SPMI. Okay, let me talk a little bit about this here. So that is not surprising. You know that in video 1 I showed that WOP and PMI are two equivalent statements regarding the set of natural numbers. And now I am saying that, okay, I was able to show that WOP implies the strong principle of mathematical induction, and I just showed that PMI itself can also imply SPMI. This is not surprising, because if these two statements are equivalent, so if one of them can imply something, some statement, it's not surprising that the other equivalent one can also do the same task. Okay? But what is a little bit surprising, that in mathematics it is common when you say I have a strong statement, what you mean is that that strong statement implies the other one. But it seems that this is the other way around here. I am saying that the principle of mathematical induction is implying the strong principle of mathematical induction. In the next video, I will show that this is actually the case, that SPMI also implies PMI. And then surprisingly, these two statements are also equivalent. So if I combine this thing, which is coming in the next video, and this that we just got it here in this video, then it means that PMI is actually equivalent to SPMI. So in principle, whatever can be proven by PMI, it can also be proven by SPMI, or the other way around. So this is what I'm saying, that when so whatever you can prove with the strong principle of mathematical induction, in principle you can also prove it with the principle of mathematical induction itself, but you need to do some more work to make it done. Okay, but if you start from a strong principle of mathematical induction for some kind of examples that I will give you one of them right now, it would be easier for you. Okay, and then so this will be finalized in the next video, but then if you take that one for granted, then we will have three statements: WOP, PMI, and SPMI are all statements regarding the set of natural numbers, and all of them are equivalent. One of them implies the other and the other way around. Okay? Okay, now let me finalize this video by presenting an example so that a strong principle of mathematical induction would be very helpful to prove it. Of course, this is the very well-known fact from number theory, showed that every natural number is either equal to 1, or is a prime, or a product of primes. Okay? Okay, so let me write my predicate first. I want to apply the strong principle of mathematical induction on this predicate. The natural number n is either equal to 1 or is a prime or is a product of primes. Okay, so this is my predicate. I want to show that this predicate satisfies the first and the second property of the strong mathematical induction. Okay, so the first statement, I need to show that P of 1 is true. But let me read P of 1. to save a little bit of time, so let me just read it orally. So what is P of 1? I want to show that P of 1 is true. It means that I need to go to my predicate, I need to replace n wherever I see it with 1. So the natural number, instead of n you put 1, is either equal to 1, or is a prime, or is a product of primes. Of course, in this case it is clear that this number 1 satisfies the first property, so it is true. Yes? So let me, by this explanation, let me just write P of 1 is true since 1 is equal to 1. Okay, now I would say let k belongs to n, and let all of the following statements be true. The statements P of 1, P of 2, up to P of k minus 1, P of k. I'm assuming that all of these statements are true. We show that P of k plus 1 is true. This is the goal, yes? If I can show this, then I can use the strong principle of mathematical induction, and this means that the P of n is true for all natural numbers n. But if you don't mind, let me write P of k plus 1 explicitly again here. So what is P of k plus 1 that I am going to prove its truth? Okay? The natural number, so what I need to do, I need to replace n with k plus 1. The natural number k plus 1 is either equal to 1 or is a prime or is a product of primes. Yes? So this is what I want to show, that it's a true statement. So to prove that P of k plus 1 is true, because this is disjunction, either equal to 1 or a prime or a product of prime, this statement is true if at least one of these statements is true. Of course, for k plus 1, this statement cannot be true. It is actually false, yes, because when k is a natural number, k plus 1 starts from at least 2, so it cannot be equal to 1. Okay? But still, there is a chance that this statement in total is true. Okay, now I am telling you that if you accept that P of k plus 1 is a prime number, then we are done. Okay, so k plus 1 cannot be equal to 1. And I always say that if k plus 1 is a prime, then P of k plus 1 is true, and we are done. Yes? But what happens if k plus 1 is not prime? So let us assume that k plus 1 is not a prime. We show that k plus 1 is a product of primes. Okay, So you say that k plus 1 is not a prime. So what does it mean? From this sentence, I can conclude that k plus 1 is a composite number, so it can be written as a product of two numbers a and b for so let me write where a and b belongs to the set of natural numbers, and moreover, of course, if this is a product, so one of them should be the smaller number, so let me call a the smaller number and b the bigger number. So then this means that a is less than or equal to b, for example, but this is strictly smaller than k plus 1, and this should be strictly greater than 1. So if you say that k plus 1 is not a prime number, and it is not equal to 1 evidently, it should be a composite number, so it can be written as a product, in which these factors, one of them is less than or equal to the other one, so I named the smaller one a and the bigger one b, but this is clear that b cannot be equal to k plus 1, because if b is k plus 1, then a is equal to 1, so it means that this is not factorized in the first place. Okay, but if you don't mind, instead of k is strictly smaller than k plus 1, I can clean this and write less than or equal to k, and instead of writing strictly greater than 1, I can clean this and write 2 less than or equal to a. Okay? So when you say that k plus 1 is not a prime, then it means that k plus 1 can be written as a product of two numbers. Those numbers are natural numbers, and then they satisfy these conditions. Okay? But now this is the power of a strong principle of mathematical induction. Oh, sorry. If I ask you, what can you see these numbers a and b in this list? Yes, because you see all natural numbers are in this list from number 1 to up to number k. And I know that a and b are two natural numbers starting from 2. We don't know the values, but we know that they lie somewhere between 2 inclusive up to k inclusive. So what I'm trying to say is that you see that P of A is one of those statements that is in this list. P of B is also one of those statements that is in this list. And then we assume that all these following statements are true. So therefore, P of A and P of B are both true. So that is the power, you know. In the principle of mathematical induction, I only know the truth of this one. But here it is not enough for me to know only the truth of the last one, because here A and B, there is no guarantee that A and B are this last one. Even one of them can be the last one. But if the other one is strictly less than B, which is possible actually, then the next one is not the last one. So at least I will have two of them. I need the truth of two of them. So therefore P of A and P of B are both true. I hope that you understand what's going on here. A and B are numbers between 2 and k, and I have all these statements guaranteed to be true by assumption. So it means that P of A and P of B are both true because they lie exactly in this interval. Okay, so then what can I say? Now we realize that P of A is true. So let me write it. P of A is true. So it means that, let me read P of A. What is P of A? P of A means the natural number A is either equal to 1 or is a prime or a product of prime. But we know that A is not equal to 1 because it is greater than or equal to 2. So there are two possibilities for A. So this means that A is either a prime or a product of primes. And then we know that P of B is true as well. So this implies that B is either, again, B cannot be equal to 1, so there are two possibilities for this to be true. B is either a prime or a product of primes. Okay, so let me finalize this orally here. So about this k plus 1, I have four scenarios going on. A is prime, B is prime. A is a prime, B is a product of primes. A is a product of primes, B is a prime, and both of them are primes. Both of them are products of primes. Yes? So, but in all cases, I am done. Yes? Here, let us assume this scenario. A is a prime, B is a prime. So then k plus 1 is the product of two primes. So it's a product of primes. If A is a prime, but B is a product of primes. A is a prime, B is a product of primes, but if you look at A times B, again I have a product of primes. The same scenario goes on when A is a product of primes and B is a prime. And finally, if both of them, both A and B, are products of primes, so this is a product of primes, this is a product of primes, so this new product, which is k plus 1, is again a product of primes, and we are done. Okay, so in all cases, we learn that k plus 1 is a product of primes if k plus 1 is not a prime in the first place. So, and then hopefully you see that this strong principle of mathematical induction is actually very powerful here, because I was not able to prove this immediately using the principle of mathematical induction, because in the principle of mathematical induction, what I know is that P of k is true, so I know that the statement is true for k, and I want to prove the statement for k plus 1. But if I want to use this strategy, I write k plus 1 as a product, but then it is not under my control anymore that these two numbers are the previous number. No, we don't know. What we know is that A and B lie somewhere between 2 and k inclusive. But we don't have any other control on which what are these numbers. So this is why just knowing the truth of the previous number k, there is no guarantee that I can show this the truth of k plus 1. Yes, so that is the importance of this strong principle of mathematical induction. I hope that this video have been useful for you. So I would appreciate if you can subscribe to my channel to support me, and if you think that the video is useful, I would also appreciate that you can give me a thumb up. Below this video I will put the PDF file, the link to the PDF file of these notes that now you can see on your display. Until the next video, be safe and goodbye.